In this lecture, we're going to be talking about Kirchhoff's current law. So there are two laws that are named after a German physicist of the last name Kirchhoff. One relates to current and one relates to voltage. So we'll take a look first at the current law. Now this law is pretty straightforward, but it's very, very important in analyzing circuits, as we will see in the next couple of lectures when we start taking a look at the analysis of circuits. So basically what Kirchhoff's current law, which I'm going to call KCL, says is that the algebraic sum of the currents entering and leaving a node need to be equal to 0. So as given by this equation here on the right. So we're saying the sum of currents as j goes from 1 to n of I sub j of t is equal to 0. But now it's a little bit convoluted. So let's take a look at this circuit to see how that works. So first I'm going to define one node here between resistors R1, R3, and R4. And so notice that now we have several resistors. We don't just have 3 as in the previous example that we looked at. And I can also see that in this node I'm going to have current I1, which is flowing from this voltage source through this resistor. This is going to be entering the node. So I1 is going to be, again, entering this node. Now current I2, which is coming from voltage source V2, is going to be entering the node as well because it's flowing from the voltage source through these two resistors and then into this node. So I2 is coming right here. And now I3 is leaving the node and it's flowing through resistor R3. So what this equation is saying is that I1 plus I2 minus I3 needs to be equal to 0. So now notice the signs that I've used. I made both I1 and I2 positive because they're entering the node. And I made I3 negative because that's leaving the node. Now that's just a personal preference. You could say the other way around. You could say that currents entering the node are going to have a negative sign and currents leaving the node are going to have a positive sign. You could say that, but I personally prefer, and I've seen it most commonly used, to say that the currents entering the node have a positive sign and the currents leaving the node have a negative sign. But the important thing here is that remember that current is the flow of charges. So if we have charged particles entering the node from two sides, then we need to have a equal but opposite flow of charge leaving the node. So one analogy that people sometimes use is, let's say that you have a street to which cars are merging into. So let's say that you have this street and then you have one car over here flowing this way. And then you have another car here that's merging into that street. Well, this point right here would be our node. So after that, then we're going to see the two cars leaving that node. So basically all we're saying is that if we see two cars coming in, then we're going to see two cars coming out. There's nothing that's staying in that node. Same thing happens in our circuit. So if we look at one node specifically, then the currents that are entering need to be equal but opposite in magnitude to the currents leaving that, such that the algebraic sum of all the currents in that node are equal to 0. So next, let's take a look at an example of how we can use this law to calculate currents in a circuit. Alright, so now that we've defined what Kirchhoff's current law is, let's see how we can use that to analyze a circuit. So in the circuit I've drawn here, we've been given the current that is being outputted by the voltage source. And we've been given a few other currents. So we've been given the current that flows through resistor R2, and we've been given the current that flows through resistor R5. But we have two currents unknown, the currents flowing through R3 and R4. So we're going to use KCL to be able to find those two currents. So first, let's use KCL at this node right here. So we see that we have a current that is entering the node, which is equal to 1 amp. And then we have two currents that are leaving the node. One of them we know what it is, so minus 0.2 amps for this current leaving the node. And then minus I3 because I3 is also leaving the node. So minus I3 is going to be equal to 0. And then we can solve for I3. So I3 is going to be equal to, we're going to move I3 to the other side of the equation. So we'll get that I3 is going to be 1 amp minus 0.2 amps. So I3 is going to be equal to 0.8 amps. So if we look at this intuitively, we can kind of see that that's going to be the case, because we have 1 amp coming in, 0.2 coming out, so the rest needs to be leaving that node. So I3, we can kind of see from this that it's going to be 0.8 amps. Now to find I4 now, we can use KCL at this node. So we have I3 coming in, but we know that I3 is going to be equal to 0.8 amps. So 0.8 amps. And then we have 2 currents leaving the node, minus I4, which is the one that we don't know, minus the other current, which is 0.1 amps. So this is coming this way through R5. So minus 0.1 amps is going to be equal to 0. So again, we can solve for I4, and I'm just going to move it to the other side of the equation. So we'll get that I4 is going to be equal to 0.8 minus 0.1 amps. 0.8 amps minus 0.1 amps. So this is going to be equal to 0.7 amps. So we can see how we can start analyzing more complex circuits by using KCL. So next, let's take a look at Kirchhoff's voltage law.